So I am going to be talking to you about automating architectural risk analysis with the open threat model format. Before I do that, I'd just like to spend a couple of moments just talking about myself. I'm the VP of product at Iris Risk, and as Glenn said, I've got a bit of a background in open source threat modeling for the last 6 years, cloud security, all that kind of jazz. So the title of the talk contains the word architecture and risk analysis. So I'm going to start off this talk just laying some foundations about what we mean with architecture. On the screen, you can see 3 example definitions. There are others. The first one, and I'm not going to read through all of these slides, of course. The first one provided by Gartner is quite simple and intuitive and probably quite familiar. It's the obvious kind of the first thing you tend to think of when you think of architecture in this context. The second one I think is a little bit more interesting though. That's really talking about there's no one single view of architecture, and depending on what you're looking at, our understanding of architecture can vary. So there's architecture when we think of in terms of infrastructure, but there's also the application design architecture, maybe the choice of threading or some other core aspect to how you built an application. And the boundary between those types of architecture is blurred and quite fuzzy at times. The third definition, however, is probably my favorite, which is from Martin Fowler, which is, fundamentally, architecture are the decisions that you wish you could get right early on in a project. They are typically the hard to undo stuff. There's some sort of foreshadowing going on here. And then unfortunately, they're often these kind of decisions that you aren't necessarily any better at making early on. So, architecture is inherently a hard problem. So that's a bit of an understanding of what we mean when we talk about architecture. So what's architectural risk analysis? Well, probably the more familiar term for that is threat modeling, or in general, secure design. There's obviously a ton of security tools out there. And processes, of course. There's SAST and DAST and pen testing and the SIEMs, etc. One of the challenges with cybersecurity is that it often focuses on the particulars. So, there's a particular vulnerability in a particular line of code, or a network's connecting from A to B on port C, or there's a particular exploit against some version of a product. And that's all good. That's all completely necessary, but it's not sufficient. So it misses the bigger picture of things. It misses the relationship between things typically. So threat modeling, it's not the only process out there, of course, but threat modeling as a practice allows you to take a step back, look at the bigger picture, and as it says here, focuses on the forest rather than on the trees. I'm sure everyone on this call is probably aware that insecure design has now been included in the OWASP top 10, which is absolutely amazing. It's important because we differentiate between design flaws and implementation defects. And we do that for a reason, because they have different root causes and different remediations. So a secure design can still have implementation defects that lead to vulnerabilities that can be exploited, which is fair enough. So you still need your SAST and your DAST and all that kind of stuff. But an insecure design cannot be fixed by a perfect implementation. So because the controls and things like that you need aren't even considered at that point. So you can't, it's sort of a bit of an asymmetrical problem in that way. I'm not going to spend too long talking about the ins and outs of different threat modeling practices. There are many different interpretations of what threat modeling is or how to do it. If someone's not particularly familiar with what threat modeling is, I'll just spend a couple of seconds talking about it using Adam Shostak's 4 questions, because I think this is probably one of the most useful general frameworks for describing threat modeling. So in short, 4 questions. What are you working on, or what are you building? What can go wrong? What are you going to do about it? And did you do a good job? So the first one's really looking at the scope. Typically in a manual process that involves looking through documents or looking at whiteboards and designs and pictures and things like that, and understanding what is this thing that we're threat modeling. The second question, what can go wrong? That's the process of identifying potential threats. As long as they're plausible, they're probably in scope of threat modeling. We don't want to do that sort of movie hacking stuff necessarily. But that's the sort of think like an attacker space. Now, it's all good fun. Finding threats is great fun, but if you're not doing anything with those threats that you found, there's probably not much point in sort of cybersecurity navel gazing at that point. The next question then is, well, what are we going to do about it? Well, we want to find mitigating controls and implement them. So, I can do X in order to eliminate that threat, or I can do Y to mitigate it, or I can transfer this to another sort of a legal entity or in some way. And typically, output of this process is non-functional requirements or Jira stories and things like that. And then the fourth question is sometimes neglected, but equally important, which is, are you doing a good job, or did we do a good job? And that applies to all of the first three questions. Are you looking at the right stuff? Are you threat modeling the right stuff at the right scope? Are you finding the right types of threats, or do you sort of have a bias towards one type of threat based on your experience? Are you finding enough possible controls for those threats, and are you actioning those controls, or have you just got a backlog of unactioned and neglected Jira stories? So that sort of sums up the threat modeling process in the general sense, and often it's quite a manual process. Probably don't need to spend too long rambling on about the arguments for shifting security left. I think it's a fairly well-established idea now that we need to do better at moving security left. So I'll start from the right-hand side, from inside the sort of that production and maintenance phase. We all know that it's very hard to make changes there, and it's very costly. Once something's in production, it can be massive pain to have to rework it or refactor it, and typically involves, throwing developers at a problem for a long period of time. So shifting left slightly, you get into where you see a lot of stuff happening around security at the moment, which is putting stuff into pipelines, into the CI/CD automation side of things. And that's great. It's definitely a step in the right direction. Just doing a pen test on something that's already in production is fine, but not as good as being able to do the stuff automatically through the CI/CD pipelines. But it's still relatively expensive to fix it at that point, because you've already built most of this stuff. Typically, it's maybe going through pre-production or going through some sort of integration testing at this stage. So you're already quite far down the process to find that there's an issue. So this is where you typically see projects being delayed because they're finding issues just before release, and it's pushing things back. So in that sense, the further left we shift, the better, and that takes us into that kind of design and development phase. So very cheap to fix issues. If your design is nothing more than a whiteboard diagram at the moment, then a fix there from an architectural point of view, for example, is to just redraw the diagram slightly. It costs you virtually nothing. And it's also a good time to identify requirements and proactively drive those into the development stages. So if you're thinking about what could go wrong, and your controls are then, not go and fix this particular issue, but go and add this non-functional requirement to make sure this thing is well designed from the start. But the downside, or one of the downsides to this, is that it can still be quite an expensive manual process. So threat modeling in that design phase often involves workshops and getting lots of very smart and very expensive people into a room for lots of time and identifying different sort of threats and countermeasures and things like that. So you kind of want to be able to speed that up a little bit. But that's not the focus for too much of that. There are some other interesting challenges that the architecture in the design phase also has to face. Very traditional ones. So architecture lives outside of the code. It's a Visio diagram or something like that, or it's a Confluence page. There are other collaboration tools out there. It's typically always out of date. Almost the minute someone starts implementing something, the original design, the original architecture is pretty much out of date, and so the implementation drifts over time. But there's some other newer emerging challenges with this whole architecture thing. What happens when the architecture disappears and you have things like serverless, where you're just deploying chunks of code? All of the infrastructure that runs that has sort of evaporated. And the same kind of thing with microservices and things like low code and no code, what else going on there? So what happens is the architecture starts emerging more from the code rather than from the cables. We don't have to worry about the underlying infrastructure anymore, because we've sort of built on top of that, but we do have to worry about how things are connecting in a different level. And what you see typically happen at this point is things like serverless exposes the application side of the architecture because the infrastructure side of things has been hidden. So how Lambda calls to each other in other AWS services, for example, is exposing some of the internal workings of that application. So your functions are relatively straightforward. So again, blurring that boundary of the type of architecture we have to deal with. And we have increasingly complex environments, fuzzy requirements, and faster iteration, increasingly demanding customers, et cetera, and that drives agile practices and DevOps and all that jazz that's making this whole thing a lot faster. So the traditional approach of architecting something and then it being developed for 2 years is long gone, as we all know. Yet, when we talk about software development, we often think of it as being like manufacturing. We use the same kind of terminology, like pipelines and batch and work in progress and deliverables and all that kind of stuff. You have this developer, this conveyor belt of Jira stories that people work on, and then some sort of sprint planning happens over there. But actually, analogies gone wild here. Software development is a lot more like art than it is manufacturing. And this is because manufacturing of a piece of software actually happens in the CPU at the point of execution. Everything up until that point is basically design. There's a fantastic paper by Jack Reeves in 1992. So bear in mind, this is nearly 10 years before the Agile Manifesto was released. Goes into a lot of the detail, but coding, debugging, testing, that is all fundamentally a process of design, not a process of manufacturing. The commit strip on the right here is also, really driving this point home. A piece of software, even a binary, is a specification for how to achieve a particular problem in a particular domain. So it is not a product in the same way that a car is a product. It is a specification of how to solve a problem in a particular set of circumstances in the CPU. And what that means is software development as a practice is essentially continuous, iterative, and revisionist design. When you're writing software, you're describing and sharing ideas in a way that lets you collaborate with people. You're learning how to solve a problem. You're reasoning with yourself and with other people. And so when you're writing code, you're not writing it really for the CPU. Otherwise, we'd all be using sort of machine code, assembly, or even deeper. We write in high-level languages. We use abstractions as objects because it helps us think about and talk about and reason about and share design. Now, not absolutely everything is a pure part. Not all of software development is purely design, and we can use tools like the Knevin framework to look at why. We'll come back to why this matters in a little bit, but I just need to set a little bit more sort of groundwork in terms of where all of this stuff is coming from and what this means in terms of automation and the evolution of sort of building on top of existing concepts. There's a lot going on this slide. I won't spend too much time here. The Knevin framework basically helps us think about different types of systems in different ways. And in this case, we're looking at it from the perspective of software development. It splits the world up into two: clear, which is things are very simple, things are very linear, if A then B, if C then D. So that's the place of best practices and checklists. Complicated. Here, there are still things are still linear, things are still predictable, but it's not straightforward. You may need an expert, you may need to do statistical analysis or something to understand, and 70% chance that A is better than B, etc. On the left-hand side, we have the complex domain and the chaotic domain. Complex is where things are no longer linear, things are coupled, they're dispositional, they tend to A and B, but you can't know that in advance. It's only with hindsight that these things start to make sense. And from a software point of view, this is where a lot of, as we'll see in a second, a lot of stuff happens. And then chaos is where it's not statistically random in that sense, but this is where things are completely non-linear as well as non-constrained. So things are just a mess. And that middle one, confused, is where you don't know which domain you're dealing with, which is a state a lot of us are in a lot of the time. And the general point here is how you solve a problem depends on the type of system you're in. So if you're there's no point doing linting in a complex space because it's completely misaligned to the nature of that system. And likewise, you wouldn't sit there sort of prototyping brand new approaches to just a simple checklist problem, because that would be a complete waste of effort. So how you think about different problems depends on the nature of the system you're in. This is a Wardley map. Hopefully people are familiar with this, but it's gaining momentum still. It has some familiarity with the notion of Knevin. You can sort of potentially map genesis to complexity and commodity to that clear domain. But what the Wardley map does is it shows you a value chain of, how you're delivering value to a user, a customer in this case, and where those different points are in that value stream and how they map to different stages of evolution. So when something is brand new, it's very little is known about it. You typically have faster iterations, a lot of learning. So that's sort of the genesis space. And then things evolve over time, sometimes in the many decades to what becomes commodities. So these are things we take for granted, very well established, very slow to change, a lot of automation and things we take, like I said, things we take for granted. So electricity used to be genesis. It used to be brand new as a concept, but over the last few hundred years, it has become a commodity. And you feel the pain when suddenly your power goes out and you have no electricity. You suddenly realize how much you've taken it for granted. But it doesn't change either. I don't wake up one morning to find that the voltage has changed from 240 volts to 173, for example. So Wardley mapping exposes these dynamics. And to bring it back to the security, the software domain, you're using cloud compute because you don't have to worry about the details of physical hardware, or even you're using Lambda and things like serverless because you don't have to worry about the details of the infrastructure. Cloud has basically commoditized the ability to do compute. And that's fundamental because it allows you to focus on the stuff that matters. And here's the fun part, of course. Things evolve over time, and you wouldn't spend hundreds of development hours trying to write a YAML file parser, for example, from scratch. You go and use a library because it's a solved and known problem. When things are well understood, they're available as products or even commodities. So what you as a software development team are left with is all the novel and domain-specific stuff you can't just outsource to a product or to a library or to a commodity. So you are left with all the stuff you have to deal with in that genesis space and that custom space. So you're dealing with the unknown, you're dealing with having to solve problems for the first time, even if it's just gluing different products and commodities together in a different way to solve a specific problem. And the process of navigating through novelty is design, hence why software development as a practice is predominantly design, unless you're just re-implementing a well-known algorithm. Anything that involves trying to solve a new problem that is not understood yet, and that's why we have product development practices, etc. This is all what drives software as a design practice. And of course, if software development is continuous, iterative, and revisionist design, then that means threat modeling needs to be continuous, iterative, and revisionist. So hopefully it is, but generally speaking, it tends to still be that sort of waterfall approach. And this is a problem for architecture because architecture as a discipline comes from that it's very well suited for waterfall, very well suited for doing that upfront analysis. But this is why we see that implementation drift, because it's hard to continue to manually maintain architecture in the same way, in a way that is aligned to the design nature of software, and therefore threat modeling sort of suffers as a result from that. But all is not lost. We have cloud. So one of the side effects of cloud is that we have infrastructure as code, and that's awesome. Because at this point, the code becomes the design and becomes the stuff that's deployed. So all of the architectural stuff that used to be a diagram somewhere that was never up to date is now actually represented in something that is both the design and the actual manufacturing, the actual execution. And as I said, sort of microservices, if you're doing infrastructure as code for microservices, what was once a monolith running inside a single web server, for example, like gigantic Java app running in a web server, if you're using microservices deployed in the cloud, then suddenly that architecture is explicitly defined in these infrastructure of code files or templates. And each of these things have their own different requirements for data transport, authentication, etc. And so infrastructure as code allows us to string together these different pieces and view this architecture in that sort of real-time way, in line with the actual pace of development through infrastructure as code. So Why an open threat model format then? Well, as we said, architecture is often defined in many different formats. It's some people have Visio diagrams, some people have whiteboard diagrams. So we need something from a threat modeling point of view that's agnostic to those sources. Threat modeling as a practice itself also needs to evolve, and one way to do that is to build open standards that people can build on and use and relate to, and that can accelerate the standardization of something that builds on top of infrastructure as code from a threat modeling point of view. One of the other challenges we have with threat modeling is, and to some extent this is necessary and is always going to be the case, there are different interpretations of threat modeling, and that makes sense because different circumstances require that. But we also need some really good common ground, and if we can do that in a data format, then that allows us to create interoperability and the ability to exchange information much easier. So organizations need to be able to exchange this kind of information either within themselves or ideally with other, and we'll look at that in a second. And so an open threat model format, put it in the open space, make it widely adopted, that could provide this common ground. So some potential use cases. If I'm thinking about trying to threat model something, I may have different sources of that design. So that design may come from an actual diagram of some sort. Maybe very early on, someone's using Visio or some other things like Figma or Miro boards. Maybe we want to be able to just take that. Yes, maybe it's out of date quite quickly, but at least if we can get into a threat model very quickly, we can evolve and build on top of it once it's captured. CloudFormation, Terraform, obviously that stuff is sitting in code. That stuff we need to be able to keep up to date with. So if we can pass those sources of architectural information, we can threat model continuously and iteratively as well. And then there's a whole bunch of other stuff out there like Docker Compose, Kubernetes, Jira Stories, and the application code itself. These different types of sources, you wouldn't want to have 10 different ways of threat modeling 10 different sources. You want to be able to bring this stuff on under the same roof, so to speak. And then once you've got to that process, to that point, you may need to be able to exchange this threat modeling data with other parts of the cyber ecosystem. So, if you could provide some context around the relationships between components within the threat model, you could provide that context to SAST and DAST and vulnerability management. So why does this vulnerability really matter? Well, because of this threat model and this context. If I can pass that from a machine point of view because of an open standard, then that, and it's not sort of buried in a 20-page Word document or something like that, then that really opens up a space for further automation across the cybersecurity ecosystem. And then finally, this one might be a bit of a pipe dream, but we're certainly seeing it within our organization. The need for organizations to be able to share this stuff with each other. So if I'm a software vendor and people are using my components, I may want to be able to publish mini threat models or aspects or components that they can then leverage in their threat models. And I can tell them, here are the threats when you use this component, and these are the mitigations that you need to implement. And we can, I can learn that as a result of using some of this content from a third party. Or maybe I want to be able to share and easily publish threats and mitigations in some way, so that maybe I've done some research and I want to be able to put it out there in a way that's easy to consume by other organizations and other tools and stuff. And a third one maybe to increase transparency. So maybe if you're doing some sort of third-party assessment, they could provide a passable threat model that you can then put into your threat model tool that looks at it and says, okay, right, here are the things you need to care about, again, rather than just reading through 200-page PDFs. So there's a lot of interesting use cases that come up, could potentially come out of a structure like this. So I'm going to now dig into the details of what exactly this looks like. We identified the need for an open specification because of working with different customers, and so what this represents is a set of expectations and a set of requirements and a set of use cases that we've seen out there, either in terms of what we see from our customers or from existing tools. So we'll go into a little bit more of that in a minute. But at a high level, we wanted something that can be malleable and flexible, but also provide enough of that standardization to make it something that can evolve. So we're trying to pull from the Wardley mapping side of things, we're trying to pull 20 different threat modeling formats further to right into that, let's say, product space, even though it's an open source thing, into that product space so that others can build on top of, so that innovation can happen on top of it. Maybe one day we'll get to threat modeling as a commodity, but probably not quite yet. So in terms of the specification, it's YAML, or JSON. So, building on the X as code momentum, we wanted something that could be committed into Git, could be diffed, and you have a changelog associated with it. It could be generated or written by hand, of course. So fairly standard arguments for using YAML and JSON for these kind of things. So the other thing is you want this kind of stuff to be able to live with where the stuff matters. So if I've got an infrastructure as code, bunch of CloudFormation files, for example, I don't want my threat model necessarily being somewhere over there. I want to be able to keep it close to my code. So having it as YAML alongside the code is a way of doing that. Inspired by OpenAPI, so it should look relatively familiar in the style. Doesn't use the sort of the Pythonic conventions. It uses more of the sort of snake cases of OpenAPI. And I'll just briefly talk through some of the different bits that make up the specification, and pretty much the rest of the talk we'll be going into more of the details on those. So at a very high level, we need to know some stuff about the stuff that we're threat modeling. So the project metadata, what is this thing that we're threat modeling? What does this threat model represent? So that's the name and the description of the application or the product or the service or whatever. Representations are an interesting one. A big complex system can potentially be represented in a number of different ways. You may have an architecture diagram, you may have a user interface diagram, you could have infrastructure as code or application code or Jira stories. These are all different representations of fundamentally the same thing, and different representations being threat modeled in different ways gives you different outcomes. So a threat modeling specification needs to be able to handle multiple representations. Assets, these are the things that you care about, sensitive information like PII or PCI data or some other thing of value. Components, these are the sort of the building blocks of any sort of representation. These are the things like EC2 instances or API endpoints or chunks of code that make up together a sort of a representation for a particular system. Trust zones, familiar terminology in threat modeling, but I don't think it's a universally used term. Typically, these are the differing levels of security within a system. You don't put your database out on the public internet because it's got sensitive data. So you go through various tiers with each introducing layers of controls. And there's relative differences in trust between those different tiers. Data flows, obviously, kind of speaks for itself, how information and assets move around a particular system between those components. And then, of course, we've got the threats and the mitigations. It wouldn't be a threat model without threats and mitigations. So what are those things that can go wrong, and what are we going to do about them? A couple of other cool things about the schema at a high level. All of the objects can have these arbitrary attributes, which you can use for whatever you want. So you could have custom IDs or URLs for documentation or anything like that, or maybe some specific measurable quantitative attributes that make sense for your implementation. The specification does, however, provide some basic risk-related properties like the CIA triad, confidentiality, integrity, and availability, some trust zone ratings and things like CWEs and likelihood and impact. Tagging allows you to group and or categorize things in some form. So you may have you may want to tag all of your AWS components with AWS. You may want to tag all of your Azure components with Azure, or maybe do it by representation instead. Different things, different representations have different requirements. So, for example, if I'm passing CloudFormation, I don't typically, if it's written by hand or generated from code, I don't have things like X and Y coordinates. So if I was to sort of draw a CloudFormation template as a threat model, I would have to interpret the layout of that stuff. And that's kind of what we're going to look at in a little bit. But if I've got some like a Visio diagram that represents a threat model, then I probably want to preserve the X and Y coordinates. So the diagram representations allow you to specify size and height, and therefore we can have X and Y components for some of those components. And another interesting thing is that trust zones and components can be arbitrarily nested. So I may have a component within a component within a trust zone, within a component within a trust zone, for example. And the general practice within the specification is to try to keep the number of required fields to a minimum. So what you'll see now is sort of a set of examples of the specification. Not all of those fields are required. That means that if you're writing something by hand, you only have to provide the bare essentials. And if you were generating stuff, then you would generate whatever you had available to generate that particular outcome. Now, while there isn't currently a single accepted open threat model format out there in the world, there are a number of existing formats for things that describe threat models. Some of these are inside proprietary tools, and some of them are in sort of open source, ThreatSpec being one of them. Probably have to update it to use OTM at some point in the future. So what we did is we obviously looked at our customer requirements and what else was going on in the threat modeling space, and looked at the other tools to make sure that a open specification was able to work in these different circumstances. Again, not going to read through every single thing here. I'm just going to call out a couple of key differences. We're trying to, on the whole, find some of the best bits of all these different tools in terms of representing threat models and some of the common bits, and pull that into a single place that can be used elsewhere. So, for example, Microsoft Threat Modeling tool, very popular still, doesn't handle different representations, and neither does ThreatDragon. ThreatDragon does support multiple diagrams, which is awesome. But for example, the mitigations aren't first-class citizens. So mitigations are a box inside a threat, whereas in this specification, a mitigation is its own object in itself. So it can be very powerful and descriptive. If you don't want to use any of that, fine, you can sort of reduce it to just a simple description, and that makes it sort of compatible with things like OWASP ThreatDragon. Similar to Threat Playbook, it's very heavily reliant on YAML, but it's a more generalized structure. And compared to PYTM is awesome, very, very flexible because it's Python. You can do whatever you want, essentially, but it's also then scoped and limited to Python, whereas this, we lose some of that power and flexibility that PYTM has, but at least it's a sort of more universal format. So I will just go through reasonably fast-paced still some of these different components, and you can see here an example of a project. So in this particular example, we have name and ID are the only required fields. So we've got some other stuff to look at as well. You'd want to be able to identify a project in a unique way. So each project would need some sort of a unique identifier that distinguishes it from other projects. So that's going to be pretty obvious, and unique IDs are going to be a recurring theme throughout this whole sort of specification. And you can see here the use of some attributes such as documentation, or probably a very useful one would be to be able to relate a project to something like an identifier in a configuration management database. So this is my identifier in a threat model, and this is where it lives in wherever I manage all of my applications, and be able to create those links back and forth between them. Representations here, we can see here an example of an architecture diagram. The type field allows you to interpret the representation in the right way. So as we said before, a diagram can have spatial context, width, height, X and Y, that doesn't make sense for code. So we want to be able to say, right, this representation is of a type diagram, and therefore here are some properties associated with that. If you don't want to provide them, you don't have to, of course. Likewise, a different representation might be application code, which is of type code, and that would have other attributes that are relevant to that type of representation, such as the repository. So if I've got application code, I need to know where that lives, and I can sort of provide that as URL. Attributes, using these custom attributes can also provide additional context, tools, and processes. So one cool thing about being able to provide context like the language or maybe some framework information inside the specification means that maybe that can trigger certain SAST or DAST rules, or maybe some sort of policy as code implementation could sort of be scoped around some of these attributes. Example of an asset then, credit card data, obviously a fairly classic. As I said before, these are the things that matter to your organization or to your users or your customers. And in order to be able to describe how important is this asset to us, we can use the CIA triad and provide a very, very simple but reasonably flexible quantitative approach to specifying risk for an asset. So we can say confidentiality on a scale of 0 to 100, and the same for integrity and availability. So where you have an asset that is absolutely fundamentally critical to you across all three of those properties, confidentiality 100, integrity 100, and availability 100. If it was something that was, you know, sensitive but didn't require, you know, that uptime to be very high, you could obviously tweak the availability down, lower it down to 50, and say, okay, while we must ensure that nobody else sees this, if we lose that data, it's not going to be that critical. So maybe you've just collected some marketing data in a survey. It's got PII, so therefore it's very sensitive in terms of confidentiality. But if you lost it, you know, it wouldn't be the end of the world. And then we can provide the additional context through a comment that allows you to, you know, describe why these particular decisions have been made, for why these values are what they are. Trust zones, again, as I said, sort of separates out the components by the relative security or trust between them. So you, again, trying to find a quantitative way of describing that difference. Normalized scale, trust zone rating lets you see, okay, how does this trust zone compare to this trust zone? If I've got a trust zone of 20, which is very untrusted, talking to a trust zone of 100, yeah, that's potentially a bit of an issue if I've got that sort of relative difference. So you may need to look at some sort of 3-tier type architecture application, or you're in that sort of zero trust space. And trust zones can be associated with a particular representation. So depending on how you're looking at a particular system, you may need to invoke or ignore different types of trust zones. Now, components, this is sort of a multi-slide section. Components can be quite complex, so you need to sort of look at it from a number of sort of different angles. So usual basic stuff like name and identifier. This time we have a parent. So where does this component live? And that parent can be a trust zone, or it could be another component, hence why we have the nested. And again, there's our friend, the type. So we can interpret the type of this component. I may have multiple web services called web service 1, 2, and 3, all of the type web service, so that when I see that component, I can interpret them in a similar way because they're all functionally the same sort of thing. So think of it like a class. And then we can use tags to group and relate these things as well in a completely flexible and arbitrary way. Now, components can also have representations to say this component is associated with this representation of the system. So there's the identifier of that particular representation, like the one we saw earlier, the architecture diagram. And then we provide that additional context. So in a diagram representation, this component should have X and Y positions, or width and height, for example. Assets live on or move through components. So we can talk about which assets are either processed or stored in this component. Again, just a simple list of referring to those identifiers that we saw earlier allows you to start building connections between these concepts, from components to assets, from component to components. And of course, data flows, how data flow moves between different components. They have a source, they have a destination. Those are the identifiers of the components, and, you know, relatively straightforward. Now, threats are, in this case, first-class citizens. So they are threats in and of themselves, and we'll see in a minute how they relate to the components. So a threat could have some sort of a name and a description, an identifier. Categories allows you to categorize and structure how these threats are sort of used. In this case, we can see a couple of the elements of stride. There's a CWE's field that lets you tie this to the CWE database, the Common Weakness Enumeration database, so that we can see how this threat relates to the MITRE CWE framework. This is still within the same threat example. We also need to know, what does this threat mean in terms of impact and likelihoods? What are the risk attributes for this threat? So, maybe this is not a particularly scary threat, so the likelihood is only 50 because it's fairly complex or something like that. But maybe the impact is 100, depending on the context. So, and again, we can provide the additional context around why that number has been chosen with a comment field. And of course, as I said, there's no point threat modeling and coming up with a bunch of threats if you're not going to do anything about it. So we need to be able to capture these mitigations, and these mitigations are also first-class citizens. So they have a description, they have a unique identifier, and they have properties that can be shared and reused across the thing. So how much, the risk reduction one here is how much impact does this mitigation have on reducing risk? Normalized value, 0 to 100 again. How you interpret that as medium, high, low, whatever, is up to you, but we just provide a sort of a very basic way of being able to describe how impactful a particular mitigation can be. And using those attributes to tie these mitigations to things like standards or other components or other data sources, or maybe even sort of, you could even link it to training material, for example, through those attributes if needed. Now, going back to the components, we obviously need to be able to relate threats and mitigations to those components, because we were just looking at them by themselves. So we can, under a component, we can say, these are the threats that matter to this component. Here's the state, it's exposed, it's mitigated, or whatever that looks like. And here are the mitigations for that particular threat. So this is one that's been implemented and this one hasn't. And the same thing applies to data flows. It's maybe slightly unusual. I think the Microsoft Threat Modeling tool allows you to associate threats and mitigations with data flows. But again, it gives you that capability and that flexibility to say, if my data flow is from a type of, and this would be in your own interpretation, implementation of a tool, if my type is of web server on the source and database on the destination, then the SQL threat may apply to this particular data flow, the SQL injection threat, sorry. And therefore the mitigations are, use an ORM or don't concatenate your strings. So I've got just over 5 minutes to go. Oh no, just under 5 minutes. I'm just going to do a very quick demo of what this looks like in practice. We've got an implementation that we're building, and I'll just show a couple of screenshots, and I'll also show what that looks like in terms of the IDE. So I will just have to change my screen share to the whole desktop, I think. Right, so over here, I have a very simple, again, hopefully everyone can see this. I have a very simple OTM file, Open Threat Model file, got the version number in there. We just have 2 trust zones. You can see here the relative rating and a number of components in here, stripped out all the other stuff that doesn't really matter. If you were to then pass it, you could visualize this in GraphViz or any other tool, and in this case it would look a little bit like this. So you can see our 2 components inside the inside their respective trust zones. At the moment, in our although it's in the specification, in our implementation, we don't have with data flows. I think actually we do, but I didn't have them when I was doing these screenshots. So if I added in a data flow, you'd expect to see a line from the client to the REST API in this case. Now, what we have here is a CloudFormation file. I've stripped it back to just the stuff that matters, so it's not actually a valid CloudFormation file anymore. All of the stuff you'd actually need to build something is taken out. But you can see here we have VPCs, we have subnets, and we have VPC gateways and endpoints and all that kind of stuff. This represents a fairly typical applications using ECS in this case. There's on our public GitHub, we have a open source Python, sort of experimental Python tool that's on the public GitHub that will pass CloudFormation and generate an OTM file. So, an example of how this could be implemented. And the way this works briefly is by allowing you to specify JMES path queries and saying, this is how I expect to find this type of component in a CloudFormation template, and this is what it means in terms of a threat model. So I can go and look for AWS CloudWatch alarms, and the type of that thing that I find in a CloudFormation file, if there is one, is type CloudWatch. And I can say who the parent is, or I can go and do some clever stuff with looking up the relationship between this component and others, for example. So this is a mapping file. It's just YAML, but it's what generates the OTM from the CloudFormation. So if I quickly run this command with that open source Python script, I'm telling it it's CloudFormation, so it knows how to parse it. I'm giving it the mapping file, so it knows how to interpret this particular CloudFormation template. Well, that mapping file applies to any CloudFormation template, but you may want to have your own versions or customize it or tweak it however you need. I'm providing a name and identifier and the YAML file itself. And I'm going to save this as an OTM file. And that's it. That was relatively straightforward. It's generated an OTM file, which if I look in here now, we can see, if I just change this to JSON, we can see now this is generated an OTM file. We've got our representation, which is CloudFormation. We've got a trust zone, and we have a whole bunch of components, including the relationships with their parents, but as I said, not with any data flows at the moment. And what this looks like when you visualize it is this. So we've got our nested components, we've got our objects, and this looks much more like a architectural diagram than when you typically visualize CloudFormation. You just see all of the objects connected to each other. This is a architecture diagram that is generated from a CloudFormation template. So I think I've got less than a minute to do this bit. Where we are literally only just talking to the world about this, trying to get people's ideas and opinions. Is this a sensible approach? How would you do it? Would you do it differently? We'll get some feedback, we'll open it up and release it to the world, and then work with people and organizations, etc., to do more cool stuff with it. Going back to those kind of use cases. If you're interested in this, if it's something you'd be interested in sort of helping out with or contributing or sharing ideas about, feel free to reach out at otm@irisrisk.com. And otherwise, I think thank you very much.